Test, test, test. Okay, for people online, can you type a yes, you can hear me? You guys hear me on for those joining online? Thank you. All right, good morning. Let's get started. I have one example to finish on the Bernoulli equation, and then we'll get on to the new topic. Yeah, so this is the Bernoulli equation we started last week. It takes a format like this. It's a nonlinear equation. The n is not 0, n is not 1. We have presented the typical solution approach to solve the Bernoulli to using the substitution transformation. So let's take a look at example. Okay, we started example already. Let's solve this question using the approach we presented in the previous lecture. So this is a Bernoulli equation. If you write it in this format, and you can see basically this is your P of X, this is your Q of X, and n here equal to 2. So this is how we solve the Bernoulli equation. We divide y squared by both sides. The y squared is the term on the right side. So y squared basically is this nonlinear term. So if we do that, then we get y prime over y squared minus a 1 over y equal to negative b. That will be the first step. Okay. So once you get this, then you're gonna let u equal to y equal to u equal to y to the power of 1 minus n. So in this case here, our n equal to 1 minus 2, which is y to the power negative 1. Basically, it's this term right here. So this is your u term. And how the u term is derived is basically from here. The next step, you're going to take, actually now you have a u equal to 1 over y. Then you take a derivative of both sides. Take derivative of both sides. The other side is negative 1, y to the power negative 2, and then y prime. Okay. So now your u prime equal to negative y prime over y squared. And this term is basically the first term of the differential equation. So now you might wonder, will I always get this? Yes. right? That's the nature of the Bernoulli equation. As long as you do it right at this step here, so you're supposed to get an expression for y prime over y squared, which is the first term of the differential equation. So basically, you can substitute the y prime over y squared with negative u prime. Then the original differential equation, which is this expression here, is transformed into negative u prime. Okay, so this one here transformed into negative u prime minus au equal to negative b. So by transform, we mean the original differential equation is in terms of y. So now it's in terms of u. And also the difference is the original one is a nonlinear, and then now you have a linear ODE, first order. That's the idea of letting u equal to this term, so then you can transform it into a linear one. So this is equivalent to u prime plus au and equal to b. Okay, so now the rest of the procedures is to solve this new differential equation using integrating factor methods, which we have already learned. So I think you can practice. This is a very simple here. So now you can use integrating factor method. And so actually, you probably don't have to use that. You could also use a separating variable approach to solve this too. Okay. But in general, right, integrating factor method will work for this non-homogeneous first order linear ODE. Or in this case, you can also use separating variable approach. So both approaches should work for this question. So I'm going to leave that as an exercise to you as how to find the solution for u. And it's very straightforward approach. So your u, okay, should give you an answer as this. So b over a plus c times e. Okay, sorry, c times e to the power negative 18. Missed something here. So that's your u solution for the u. Okay, once you get the u, don't forget that your ultimate objective is to get the solution for the y. So y equal to 1 over u, and 1 over the whole term here. If you want to simplify this a little bit, that's fine. So that's a over b plus a times c e to the power negative 18. There you go. So that's the final solution for y, okay, based on this answer here. Question. Okay. So as you can see, Bernoulli equation basically involves two steps. Number one step, you transform the original nonlinear differential equation into a linear one. And then from here, you apply appropriate approach that we have learned for any on a linear first order routine. Any questions on the Bernoulli? Okay. So far, okay, so these are all the different types of first order differential equations that we're going to cover in this class. When you exercise this, at this stage, you always try to look at it in the from bigger picture. Okay? So basically, the first step is to identify what type of differential equation you're dealing with, and then you apply the appropriate technique, right, for that type of differential equation. So if I jog in mind, basically we have learned two different types involving for a linear first order ODE. And then on top of that, we have three other types. So separable equation, homogeneous equation, and then Bernoulli equation. Right? So those three types Doesn't necessarily has to be linear anymore. The other three types could all be nonlinear, right? Particular Bernoulli and the homogeneous equation. So they all, for homogeneous and Bernoulli, they all involve a substitution to transform the nonlinear into a linear one. All right, so the natural step for the next process is to learn, right, after first order, is to learn second order ODE. But before we learn a second order ODE, so we have to learn a new topic, okay, which will help us solving second order linear ODE. And this topic is about complex numbers. So I don't believe you have learned complex. Have you ever covered a little bit of complex number in any other courses? Let me know if you have. Raise your hand. No, right? Oh, well, there's one, two. Which other course? Which course have you learned complex number previously? Oh, the UBC course or you 278? We don't have 278. 178, you mean? Okay. So, well, since majority did not raise their hands, so I'm going to treat it that you have never learned before. All right. Yeah. So, complex number. First, let's get a definition here. So we use a Z to represent a complex number, A plus JB or A plus IB. Okay, so this is how you write a complex number. So let's call this is definition of complex number. All right. So what are we looking at here? So first for Z is just a symbol representing this complex number. And what we're writing down at it here, there are two terms. We call the two terms, one is the real number, and the other one is imaginary number. Or maybe I should, maybe I should call this as imaginary part, okay, real part, okay, imaginary part. Okay, so what are we talking about here is that this A here, okay, is the real part. This JB here is the imaginary part. So the writing can be equivalent. So sometimes you will see in the lecture notes, right, it's A plus JB. And sometimes you see A plus IB. So both ways are fine, okay? If you use a mathematical tool like a MATLAB, when you create an imaginary number, you can create a number as 5 plus j multiplied by 3, and you press enter, you create an imaginary number. Or equivalence, you type in this, it also create an imaginary number. Okay, so both ways are fine. So this j or I at here, we call this as a imaginary unit. Imaginary unit. So what is imaginary unit? So this j equal to I equal to negative square root -1. Okay. So this is where basically, when people start learning complex number, this is where a lot of time our brain will start to have a little bit of resistance. Okay. Yeah, imagining a few hundred years ago when complex number was first proposed. So why our brain will protest is, how could you have a negative number underneath the square root? Right, that's basically the trouble here. Okay, because for now, before this, technically before this lecture, right, whenever we deal with the square root of anything, we always assume whatever underneath the roof of the square root is a positive number, at least a 0, right? Yeah. So now we have to accept that the numbers underneath the square roots can be a negative number. And that will turn it into a complex number. Okay? Yeah. So for now, I want you to accept it first. Okay, we'll look at it, some applications of a complex number next. So first of all, there's also a name for the A, right? We call this as a real part. So we write it like this. A is the real part of this complex number Z. That's how we denote that. So A is the real part of Z. And B, you can write it as I am Z. So that's the imaginary part. So B is imaginary part of Z. So I guess, I need to probably correct myself a little bit here. So I just circle this B here. So that's how mathematical operations. So if you say, if I have a complex number, how am I able to extract the real part, imaginary part of complex? So you can use this symbol here to denote, right? That's the real part, that's the imaginary parts of this complex number. For complex number, okay, sometimes we also call it imaginary number, okay, because it's not a number that actually exists in real life, okay, or in real environment. So for a complex number, so we can illustrate using the so-called complex plane. So for a real number, right, just to jog your mind, if a real number, it's easy. You draw the x-axis, and then you can label 0, and then you can label the numbers, right, along this horizontal axis. That's how you illustrate where the real number is, right? But for complex number, because there are two parts, right? There's the real part, the other one is the imaginary part. So we have a complex plane, very much like an XY plane. But this time, you label the plane as a real and imaginary axis. Then if you have a real, if you have a complex number, for example, Z equal to A plus JB, whatever the A or B values are. So then you can go to this complex plane. So the real part is A. So let's just suppose A is here. Imaginary part is B. So let's just suppose B is over here. Then you can create the location of this complex number, which is right here. And you can draw very much like a vector, right? But this time you don't draw a vector kind of arrow line. You just draw a bar stick line here. And you can label this as A plus JB. So that gives you this complex number here as an illustration. Now, based on this graphic here, we actually have a few terminologies. So based on this graphic here, obviously you can get the total length, right, from origin to this location right here. And also you can also get an angle, okay, from here to here. So this absolute value Z, we call this is so-called modulars. So call it modulars. They're more like a vector, right? It's vector, we call it length, okay, of the vector. And sometimes you can call it length, then I understand what you're talking about, basically. Okay? But technically, this is called modulars. So obviously, what's the value of the modulars? I mean, so basically you calculate the length of this segment of line at here, which will give you essentially a squared plus b squared, right? Yeah. So that's modulars. It's basically like the way you're dealing with a vector. So you get a length of the vector. And the theta refer to the angle from x-axis, which is the real axis at here, to where the complex number is. And theta here is called argument. So we speak of the language, right? So theta is not just the angle, you know, of course, properly we call it the argument for this complex number. We represent theta using ARG bracket Z. So argument of the complex number Z. And obviously, how do you calculate theta? So you have B over here, you have A over here. So you can calculate this theta using that triangle. So that basically is a tan inverse B over A. That's your theta angle. Your angle, the range for the theta, okay? The range for the theta is between negative pi to pi. So if your line is over here, right? So that's from 0 to pi. If the line is at the bottom of the real axis, then it becomes a negative angle. So angle always counted from the real axis to where the complex number is. If you have a counterclockwise rotation for the angle, then you have a positive angle. If you have a clockwise rotation, like from here to here, then you get a negative angle. Okay, so that's exactly the convention we typically use, right, when we are doing angular angle, you know, rotations, right? You know, counterclockwise is positive, clockwise considered as a negative. All right. So this is basically the information you can extract from a complex plane. So now next is, how do we operate based on the complex number? So let's look at some operations of complex number. Let's look at some of the easy ones here. So addition or subtraction. So suppose you have two complex numbers. So when you're adding the two complex number, all you need to do is you add the real part together, then you add the imaginary parts together. If you do subtraction, it's exactly the same thing. If you subtract the real parts and then you subtract the imaginary parts. So that's addition and subtraction. So we'll look at the multiplication next, but before multiplication here, there's another one. This is a unique one, okay, dedicated to complex number. It's called conjugate of complex number. So what is conjugated here? So let's start with a complex number z equal to a plus jb. Then its conjugate is, we use z star, okay, to represent, when we use a z to the power star here, okay, superscript star, we represent, this is the conjugates of the complex number Z. In some literature, they also use Z with a bar on top. It's the same meaning. Okay, in my lecture notes, I'll use a Z star. Okay, as representing the conjugates of this complex number. And all you need to do is you flip the sign. You flip the sign for the imaginary part, so that plus GB becomes negative GB, so minus GB. So that's complex. That's conjugates of a certain complex number. To illustrate this side by side, okay, between the original complex number and its a conjugate. So if this is A, this is B, then this is your original Z. Then the conjugate basically is the reflection. It's a reflection of the original complex number about the real axis here. That's the conjugate. Okay. So a little bit comments said here regarding the conjugate. Okay. Now, as long as you're clear with the definition of the complex number and its conjugate, okay, so you can actually see some manipulations. For example, if you add the complex number and its conjugate together, so what do we have? We have A plus JB plus A minus JB, which equal to 2A. Or we can write it A as 1/2 Z plus Z conjugate. And A is basically the real part of the original complex number. So the operation over here, the addition of the complex number plus conjugate divided by 2, actually give you is the real part of this complex number Z. And similarly, you can subtract the 2 divided by 2, and now this time divided by 2J, okay, divided by 2J, and you can get the imaginary parts of this complex number B. So this is your imaginary, right? So these two operations, we actually will make use it when we, often in time, when we try to prove some of the questions, okay, in the next step. So these two, I want you to memorize it more of as a formula. Okay. So how do you get the real part? You can get it like this. How do you get the imaginary part, and you can get it like that. So that's conjugates of a complex number. The next one, let's look at the multiplication. How do we multiply two complex numbers? So unfortunately, this is not just a simply multiplication two real numbers anymore, because it involves the complex, the imaginary parts. But you still need to do a lot of multiplications for sure. Okay, so let's do the multiplication. So let's say we're going to multiply these two together. So the first step, you write as a bracket times a bracket. Each bracket contains the two complex number. Then very much like x plus y times maybe another w plus e, right? So now you multiply every terms out. Okay, so basically you multiply a1 times a2, a1 times jb2. Okay, so you can write a j at the top. So a1 times jb, a1b, j a1b2, then jb1a2, and then the last one got g square b1 b2. So you essentially it's like treating every one of the term, right? Every one of the terms in the expression as a number, okay, and then you multiply them out. So J is a complex, is an imaginary number, but still, okay, you're treating it as numbers, so it's J squared. And then you can simplify the terms out of here. You group all the terms that are imaginary terms together. Okay, so these terms are imaginary because they have a J in front of them. So that's J A1 B2 plus B1 A2. Okay, so now you group them together. And A1 A2 is a real number, so you can put it there. Now J square term here, right? J square. So if you recall, the J here is square root -1. So J square basically is a square root -1 square, which give you back this -1. So that term over there is minus B1, B2. So that's the end of the operation of the multiplication here. So you basically, when you multiply two complex numbers together, you're supposed to get back with another complex number. That's the idea. So what is the relationship between complex number and real number? Right. So let's say you have a z. So if you have a real number a, you have a real complex number a plus jb. So if you look at the two expression in here, now when b equal to 0, so basically this complex number becomes a real number, right? Yeah. So I could actually say this, not very real. So complex number is more of a general sense of a number, okay? And real number is more of a special case of a complex number, right? So complex number includes the possibility of real number. As long as the imaginary part is 0, then you get a real number, right? That's the nature of the difference at here. So when b equal to 0, you get a real number. So the complex turn into a real. Okay. Now, before I talk about the next operation, right, division. So let's focus on this multiplication in here, especially this j square. So I want to elaborate a little bit about a j square at here. I'll just call this as a comment. So what is j square or j times j? Or how about j cubed, j4, right? Continue, j to the power n. How would you interpret each one of the term? How could you quickly get that number, right? So I'll illustrate like this, okay? Okay, so let's say this is your complex plane, and then you have a real axis, and this is the 1, okay, unit 1 at here. So let's start from j times 1. So j times 1 give you j, right? Yeah. So where is J? J is the imaginary number. If I just plot the J is right here, right? Yeah, that's your imaginary number J because it's on the imaginary axis. The real part for J is 0, so it's right here. So the operation, when you multiply J with the 1, okay, so let's consider this is like stick right here. When you multiply this, it rotates 90 degrees, okay, and turn that stick over here, right? Yeah. So let's continue here. So then what about J times J? Okay. So you multiply J with another J. Basically, this is your current location, right? There's J here. And now we multiply with another J here. So technically, remember what we get? -1. So where's -1? So -1 is right here. So the operation, when you multiply J with the current J, it rotates another 90 degree over here. So now you can do the next one. So how about J times -1, which is J times what? J squared, right? Because -1 equal to J squared. So J times -1 is J times J squared, which is basically your J cube. So maybe I should write it this way here. So J cube equal to J times J squared equal to J times -1. So let's write it to the other direction order here. So J times -1, which gives you -J, right? And -J is right here. So now you got another 90 degree rotation. And then finally, J to the power 4 is J to the times J cube. So that's J times -J, which gives you 1. So finally, we get back to this original location. So the point I'm making is, whenever you multiply a J with a complex number, right, or anything even, so what does it do? It will rotate it 90 degrees, basically. Okay, so this is actually application. You know, complex number. So let's suppose you have an image, and you have an image somewhere in the plane here. And if you multiply the image with J, so what does it do? It will rotate the image 90 degrees. Okay, so basically it will rotate 90 degrees. Okay, so you can imagine how it's going to rotate, right? So that's what J does here, basically. You know, whenever you multiply, you rotate 90 degrees. As a matter of fact, you can also verify if I don't multiply with a J, if I multiply anything with another complex number, for example, A plus JB. Okay? So not only it does a rotation, it also does some kind of scaling. So when you multiply with a complex number like this general A plus JB, and consider this is some sort of a graph right here, it actually does rotation and scaling at the same time. The graph rotated and then also probably becomes smaller or bigger. Yes. Yes, around the origin, yes. Yeah. And that's very widely used in computer graphics, and also sometimes in robotics application. Yeah. We also have a different concept, okay, to do the rotations, okay, when we use a rotation matrix, but it's very similar to the idea illustrated here. So having said this, I probably didn't see the applications of the complex number. Complex number, after it's discovered or formally defined, right? Nowadays, complex number are used in quantum mechanics, also in robotics applications, in aerodynamics. And you can find it's also in AC circuit, right? So when you learn AC circuit, you also have phase angle and also have magnitude, right? To talk about alternative voltage or current. Right? All of this has complex number behind it to help you mathematically, understand the concept. All right, so now let's take a look at the concept of division as operation. Complex number divided by the other complex number. Now, just like a multiplication, when you multiply two complex numbers together, you get another complex number. And when you divide the complex number together, you're supposed to get another complex number, right? So that's the bottom line. So how do we do this division at here? So here's how you do. Remember the Z1 as euro is A1 plus JB1. Z2 is A1 plus A2 plus JB2. So when you divide each other, so essentially you get A1 plus JB1 over A2 plus JB2. So the way to handle the multiplication is you try to get rid of this complex number on the denominator. Right? Notice there's a complex number in the denominator. So we want to write this complex number at the end becomes, let's say for example, becomes C plus JD. So as a standard format of complex number, real plus imaginary, right? Yeah. So then we need to get rid of this complex number on the denominator. So how do we do that? We use that conjugate concept. So we multiply the denominator with its conjugate. So you multiply the denominator with its conjugate, but you cannot change this number, right? So then you have to multiply the numerator, numerator with the same term, okay, which is the conjugate. So this way, when you multiply the denominator out, so whatever the numerator is, you can do the multiplication operations that we learned. But the bottom here, the denominator, what do we get? This is like a x plus y times x minus y, right? And what does that give you? X squared minus y squared. Okay. So the bottom here give you A2 squared minus GB2 squared. I'll let you handle the numerator. Numerator just multiplying the two complex number out. So then what's A2 squared minus GB2 squared? So G squared is -1. And you have another negative in front of it. So the bottom becomes A2 squared plus B2 squared. Okay. Now the complex number on the denominator disappeared, right? Becomes a real number, A squared plus B squared. So that's the simplification you're making here to transform it into standard complex number. Now, having illustrated this one here, let's see what do you notice, right? So if you notice on the bottom here, so what it really does is basically you're multiplying Z2 with Z2's conjugate. Right? So the bottom here, this is Z2. This is Z2 conjugate. So that's what we're doing, right, for the denominator. And then the results, right, the results of the multiplication between the complex number and its conjugates give you this A squared, A2 squared plus B2 squared, which is the modulars square, right? The square of the modulars. So this is actually, you can consider another sort of like formula, right? Try to remember. So what happens when you multiply a complex number with its conjugate? You get the modular square, very much like you get the magnitude square. Okay, so that's easy to remember. This is the division, right? So let's take a look at an example, an actual example here on division. Let's say we have a 9 plus G8 divided by 5 plus G2. So I'm going to multiply the denominator with its conjugate. So that's 5 minus G2. And top is 5 minus G2, right, to keep this whole term unchanged. Then the bottom here, right, as we have just demonstrated, when you multiply the conjugate with the complex number with its conjugate, you get 5 squared plus 2 squared. So it's a real number. And then you carry out the multiplication of the two terms of denominator. So just like the regular multiplication. So 9 times 5, 45. 9 times negative J2, so negative J18. J8 times 5, J40. Negative J8 times negative J2. So plus J squared 16. So further simplifying it, G squared is negative 1. So you got a 45 minus 16. So that's 29. And then minus J18 plus 40, 58. 5 squared plus 2 squared, so 25 plus 4, 29. So obviously you got 29 as a common factor, so it's 1 minus J2. So that's a simplification when you do this division between the two complex numbers. Okay. A couple minutes here. Let's think we can finish the next concept here. So operation-wise, that's pretty much that: multiplication, division, conjugate, right? So, you know, there's not much else to do. Okay? There's no integration, but in the future, as a matter of fact, there is integration complex functions, so called complex calculus. The next concept is the polar form of complex number. So here you will see a similarity between the complex number and the vectors, right? Yeah. So let's say we have a complex number as we illustrated. Plus JB. Then we call this is this is your modulars. This is your theta, right? So we're gonna define the modulars as R. So obviously it's square root A squared plus B squared. And theta is the argument, so let's just keep it there. Then your A here, okay, can be written as R cosine theta. It's like the X coordinate. And B here can be written as R sine theta. to like the y coordinates, then your z complex number, instead of a plus jb, now can be written as r cosine theta times plus j times r sine theta. You can take the r out as a common factor. So now the complex number can be written in a new format. We call it just a polar format. So this is a polar form. This is very, very useful, as actually a lot of time when you calculate the multiplications or divisions of two complex number, it's probably actually easier to transform it into the polar format first, and then you do the rest of the calculation. It's actually easier than the raw direct calculation. Okay. So we'll take a look at one important formula called Euler's formula based on this polar form of the complex number in the next lecture. Any questions? Feel free to come over.